Okay, folks, so we're going to continue our conversation about radicals and radical halogenation of hydrocarbons. We're going to skip over ethane. We've talked about methane in a lot of detail. We're going to talk about propane today because it gives us some complexity to address a variety of issues, all right? And basically, I want you guys to be able to answer 3 questions very effectively anytime you see a simple hydrocarbon. Okay, so the first question is going to be how many different kinds of hydrogens are on the molecule? All right, propane obviously has 8 hydrogens on it, but there's only 2 different kinds of hydrogen. Okay, so we have 2 methyl groups. Each of these methyl groups is attached to an ethyl group. So these are chemically equivalent hydrogens. Okay. We also have a CH2. This is a secondary carbon, and these hydrogens are the same as each other, all right, but they are not the same as any of the methyl hydrogens. So we have 2 different kinds of hydrogens on propane. The second question that you need to be able to answer, and this should be very rapid fire, is are the carbons that these hydrogens exist on, are these carbons tertiary, secondary, or primary? Okay, and why is that important? Because the third question that you need to be able to address is what are the relative stabilities of all of the possible radicals on all the different carbons from all of the different hydrogens that you could pull off a molecule. Okay, keep in mind that we're always talking about sp3 hybridized CH bonds that are going to be homolytically cleaved for radical halogenation. This will never happen in an sp2CH or an spCH. Okay, so you should be able to identify how many different radicals can be made, which is essentially how many different sp3CH hydrogens are there. Okay, what is the substitution on those radicals, and what are the implications in terms of stability? Okay, so bond association enthalpies. We have our chart here. Highlighted down here, we have our 101 kilocals per mole for a primary CH bond. Okay, to break that homolytically, it's going to take 101 kilocals per mole. Here we have a secondary carbon on a hydrocarbon, the 99 shown here, so it takes a little bit less energy. It takes a little less energy to break that bond because a secondary radical is slightly lower in energy. It's like lower hanging fruit, okay? Or a lower hanging stair. It takes less energy to climb up to a lower stair than a higher stair. Okay. So here we have propane. We've already done our initiation step, and we've broken up a dihalogen species, so either Cl2 or Br2. Those are the 2 that we're going to worry about. Okay. So we have our halogen radical right here. Okay. And this is going to pull a hydrogen radical off of propane. All right, so the question is it going to pull off a primary hydrogen to give us a primary radical like this, or is it going to pull off a secondary hydrogen and give us a secondary radical like this? All right, so the easy question here would be which one of these radicals is more stable? That should be a gimme question. You should know that secondary radicals are more stable than primary radicals due to hyperconjugation effects. Okay, in either case, we're generating an equivalent of HX, so whether it's HCl or HBr, okay, it's going to form that. But the reality of the situation is that when you do a reaction, you're not doing it on one molecule. You're doing it on billions and trillions of molecules, right? A mole of molecules is 6.02 times 10 to the 23rd, okay? So many zeros. There are countless numbers of molecules almost doing this, all right? So again, the reality is when somebody asks you which one of these is going to happen, when you're dealing with a mole of compound, the reality is that the answer is both. Both will happen. So let's talk about some actual experimental results. So in this case, X has been specified as chlorine, all right? And this is the radical, so chlorine radical. Right, and you might be curious why there's 2 arrows here. There's 2 arrows here because lots of things are going on here, right? So one thing that's going on, there's the propagation step that's been shown up top, all right? And then to form this, these radicals have to react with either another equivalent of Cl2, okay, in another propagation step to give this product, or there can also be a termination step in which the radical reacts with a chlorine radical again to form final product. All right, but when this reaction is done in a flask, we get the result of 40% primary chlorination, okay, 40% primary, and 60% secondary. All right, so 60% of this product mixture is coming from replacing one of the two hydrogens on the secondary carbon, while the other 40% is coming from replacing one of the 6 hydrogens on primary carbons. All right. Now, this is important because there is probability involved in chemistry. So I talked a little bit about how molecules tumble through space. Okay, when you guys threw molecules at me in Gen Chem, you saw how molecules tumble through space. Molecules have to collide with each other in a certain orientation in order to achieve a reaction. Okay, so it isn't just is there enough energy around, okay, it's also is there enough energy around and are these things hitting each other in the right orientation. Okay, so with 2 hydrogens on this secondary carbon and 6 equivalent hydrogens on the primary carbons, okay, there's about a 3-to-1 chance that something is going to collide with one of those primary hydrogens rather than the secondary, okay? So just overall probability of collision would tend to suggest that we should get more of the primary, okay? And yet we've also discussed the fact that secondary radicals are more stable than primary, all right? And this is an issue of kinetics versus thermodynamics, okay? The speed of a reaction is increased by, the probability of a correct collision, all right? So one might say that the formation of the primary radical shown here, it's actually more likely, just statistically speaking, in terms of how molecules are going to bump into each other, all right? However, we also know that this is more stable. So the secondary radical highlighted in green, this is thermodynamically favored, all right? Overall, the secondary chlorination shown here is favored, all right? So despite this conflicting thermodynamic versus kinetic preference, we have experimental data that tells us the secondary chlorination is favored, all right? So when we talk about overall reactivity or relative reactivity of the primary hydrogens versus the secondary hydrogens, we need to do just a little bit of math, okay? So the 60% of the product came from 2 possible hydrogens on the secondary carbon, okay? So that means each one of those hydrogens can account for about 30% of the overall product, okay? So 30% of the product per hydrogen on secondary carbon. The 40% of the product that is primary in terms of the chlorination product comes from 6 different hydrogens being able to do this, all right? So per hydrogen, this is 40% divided by 60, about 6.67% of the overall product comes from each one of those hydrogens based on statistics, all right? So we know that the secondary carbons, each one is responsible for 30% of the product. Each one of the primary hydrogens is responsible for 6.67% of the product. So what we do is we take 30, divide it by 6.67, and we see that in terms of, percentage, okay, the secondary hydrogens or the hydrogens on secondary carbons are 4.5 times more reactive than the primary hydrogens, okay? So just to talk about relative reactivity in terms of actual empirical experimental evidence, okay? So this is all based on an experimentally determined 40 to 60% ratio of primary to secondary halogenation. Okay, hopefully that all makes sense. All right, so this is in this case. Right, this is in the case of propane. It is in the case of using chlorination conditions. All right, so this is a specific one experiment that we have broken down and analyzed in terms of probability and stability of radicals and relative reactivity. Okay, but if we do radical bromination, right, so now X doesn't equal chlorine, it equals bromine. So again, bromine radical here for X radical. If we use bromine, you see that now we have 97% secondary halogenation versus 3. Okay, so up here we had 60-40, right? This is 3 to 2 or 1.5 to 1 ratio. Okay, 97 to 3, this is over 32 to 1 selectivity. Okay? So, doing the same kind of analysis, so we're getting 97% of our product mixture from the 2 hydrogens on the carbon in the center, the secondary carbon, and we're only getting 3% now from all 6 of the hydrogens on the primary carbons. All right? So, we take 97 divided by 2 and we get 48.5% of product per hydrogen on secondary carbon, excuse me, and we have 3% of our product coming from 6 hydrogens on primary carbons. All right, so that's only 0.5% of product per hydrogen on primary carbon. All right, so we take 48.5, we divide by 0.5, and sorry, this is wrong. Okay, this is not 4.5, that's a copy and paste error, so this should be 97. Okay, 97, and so a hydrogen on the secondary carbon is now 97 times more reactive, or another word we use is labile, okay, than a hydrogen on a primary carbon. In this case, right? So what has changed? We've gone from chlorination to bromination.